Welcome back, everybody. Welcome back to the channel. So today we're going to be continuing where we left off with our C++ integration with our programming language. So I'm going to go back here. I was doing some stuff earlier. So if we go back to our previous example, we were kind of at the low-level portion of C++. So if I go back here, we're kind of talking about this and how we actually make each connection when it comes to handshaking. So if I go back and I do a search, or actually I forgot it's all the way at the bottom. So if I scroll all the way to the bottom to the last one, we already talked about how to handshake the programming language with the library. So once we're successfully handshaked, then we need to actually try to link the function. Now, before we get into that, we're going to just get into free library because this is the easiest one. So if you want to be able to free a library, that's going to be located in the standard library. So we'll go to support 0.2.805 and then platform DL. That's going to be this free library function, which then calls the platform free library, which is also in the platform directory, kernel, and then that calls the respective system interrupt. And of course, we're going to pass in the full path, or not the full path, but the full name of the actual library. Now, the cool thing about this is that we're actually storing the full path of the library. So at any point, as long as we're passing the file, for instance, let's say we're referencing this DLL from the directory of the current directory, but then let's say later on we're referencing it in a different way. So like if we were to say, I don't know, load library underscore library of foo, and then we also said load library, but instead we said dot dot slash, some directory and then slash foo. As long as it's referencing the same file, we're good to go. So using this gitlib path actually allows it to be pretty cool and easy to use. So when it comes to freeing a library, as usual, we want to make sure that our data that we're popping off the stack, our int8 array, is not equal to null. And we also want to make sure that is in fact a variable or a numeric value. Then we convert that into a string, and then we guard the thread monitor because again, we don't want to be trying to free up the same library more than once. So in order to free the library, we say whether or not it was successful by putting that value into EBX. Then that value is then returned back at the high level as a result, and we can inspect that result at the high level in our programming language. So when it comes to freeing up a library, it's pretty simple. So all we do is I create a field of lib, and then I check for the library name. So I'm going to pass in the name, which is again going to be the full path of the actual library. And if the name matches any of the libraries we have in our system, then I'm going to assign a reference to that actual library. And I'm going to set the index as well, so that way we know where to remove it in the libraries list. So then we come down to here and we're going to we're going to check to see if the library is not equal to null. And if so, then we need to basically check for the bridge function. Now, we haven't gone over this bridge function. We're going to go over this in a second, but just know that there's going to be a bridge function, which is what we're actually going to use to bridge the gap between our programming language and C++. So in this video or this episode today, we're going to actually figure out how do I make that true connection between the high level of my language and the low level of C++. So we look for this bridge function. It is called SNB main, and we call load function, which prompts us to pass in the handle of the actual library and the name of the function. Now, load function is again a dynamic defined statement, which is based on the operating system. So for Windows, I say get proc address, whatever the handle is, and then the name of the function. For Linux, I say DL symbol, and I pass in the handle and the name of the function again. So that's kind of how it works for loading functions in the actual programming language. And then we basically want to look for any functions that have been linked, essentially. So the reason why you want to do this is because if you then subsequently call this function again after you just freed up the library that it was linked to, you're going to get an unsatisfied link exception. So that's the purpose of doing this, because we don't want to have functions referencing addresses of an actual function inside of a DLL that's not there. That's bad. You don't want to do that. So we definitely want to set the bridge function to null and the link address to -1. And that's going to be pretty much it. And then you just call a free library, you pass it the handle, and that officially frees the library. Again, this is another defined statement that's operating system independent. So for Windows, we say free library, pass it the handle. For Linux, we say DL close, and we pass it the handle as well. So that's pretty much how it works for freeing a library. And then of course we free up the name and then we remove the actual library based on the index that was set up here. So that's kind of the full function for actually freeing libraries. I actually realized that I never showed you guys how to actually link a function. I mean, I did show how the actual code works with the entire system, but I never actually went into the code. So this was actually recorded after the video. So let's just look to see what we actually do. So when it comes to linking a function, this is going to happen both automatically and manually. So if you guys remember, I mentioned in somewhere in the video where basically you have automatic linking, where when you call the function, it calls the link function automatically, or you can specify it dynamically in here. So when it comes to actually linking it manually, let's look at that first. You want to get the name of the library and the name of the function, or both functions, and you want to check, yeah, so these are both the names of the values, so they're both vars or integer arrays. And we want to create two strings from both of those. We want to guard the thread monitor to make it thread safe, then set the result into the EBX register, which again we can use at the high level to return a result value from this actual system interrupt call. So for VM link, I pass in both the name of the function and the name of the library. I get the library from our library system, and that returns the array. We've already gone over this function. It just looks for the library with the same name. And then once we do that, we for loop through the entire methods list and we look for the function name that we passed in here equal to the full name of each function in our virtual machine. And after that, we want to make sure that the function is in fact a native function. If it is not in fact a native function with the native keyword pre-appending it, then we return false because obviously you can't link a function that's not native. So we just want to protect against that. And then we say link proc, and we basically want to get the address of the link function in our actual DLL. And this video, since I'm filming this afterwards, you are going to see it because I haven't edited the video yet, so you may or may not see this link function before or after this part. So don't worry, it's going to be in the video. But once we get the address of the link proc, then we can call it. So we're going to make sure that the link proc is in fact having a value. If it's equal to 0, then obviously that means we didn't find it. And then we want to set the link address, which is just a int32, equal to the value returned from link proc. And we're just going to pass in the full name of the function, and we'll get back the address that is linked to that specific function name. We want to make sure that that value of the link address is greater than or equal to 0. If that's the case, then that means that we successfully can then basically call this function at the low level. So we assign the link address of the method that we're currently on equal to the link address. We assign the bridge equal to the actual bridge function inside of here. And we're going to return whether or not it was successful based on whether or not the bridge is equal to null. So if the bridge is not equal to null, then that means it was successful. Otherwise, it is a false. And of course, if we don't get through here, we just break out of this for loop anyway, and then we would just end up returning false naturally. So that was static linking. Now let's look at dynamic linking. So if I go to the actual virtual machine, yeah, so we're here. If I search for invoke delegate, this is going to bring us to this invoke delegate function. Now, invoking delegate functions, I've mentioned this before. Now, I kind of skipped over this because it is a big function, but let's go over it now. Basically, what you want to do is you want to set the address, or you want to pass in the address of the function you want to call, and you want to pass in how many args this function requires, the current thread that we're on, and whether or not this is a static call to an actual delegate function. Now, if it is a static call, then we will do a check here for whether or not it's a native function. Otherwise, we will complain and say attempting to call non-native static delegate function. The reason why is because delegate functions are not allowed to be static at the high level. The only way that a delegate function can be static is if it is in fact a native function. That's just a high level construct. And if you guys remember, delegate functions are interface functions where we can put those signatures into interfaces to effectively force classes to implement them. So we'll go over this in a second, but assuming that it's not a static call, then what we do is we get the sharp object by getting access to the current stack pointer minus the args, and that gives us the current object. And then we want to check to see if that object is not equal to null and it is in fact a data structure. And then we want to get the class off of that object, and then we want to basically get that from the info and assign this class field address to that class. The purpose of this is so that we can actually find where we actually need to call the actual delegate function. So we're going to make sure the class is not equal to null. And if the class is not equal to null, then we have a for loop here, and and I'm doing this twice, which doesn't make any sense. But with the for loop, we start at I is equal to method count minus 1, and then we say I is greater than or equal to 0. So we're starting from the end all the way to the front of the list. And basically, we just go through all of our functions to see in that class if methods at I and we access the delegate address is equal to the address of the delegate function that we want to call. And this is going to be assigned by the compiler at the high level when we actually call the delegate function. We'll see all of this later on. Again, this is kind of like the exception system where it's not really going to make sense until we actually build it on the compiler. But once we do that, and if that's the case, that means that we have found the actual function that we want to call. Then we basically just execute that method and return out this function. Now, if we get down to here, obviously we didn't find it, so we just set the class equal to the superclass, and then once more, go through all the methods to see where that actual function is. Now we're guaranteed to execute this function at the low level because the compiler does not allow you to create a class where you don't implement delegate functions. However, there is still a potential that you could have a delegate function that has no subscribers. So just in case, we will throw a runtime exception explaining that. Otherwise, if the class is actually equal to null, then we'll say attempt to call delegate function on a non-class object. And yeah, so once we do that, that's pretty much it for calling delegate functions. Now let's actually look to see how we dynamically call a function. So this is what the typical flow will be when we actually call the foo function, right, dynamically or just automatically, and the system will dynamically handle resolving the actual function link with the appropriate DLL. So what we do is if I go back to the virtual machine, we check to see if the method is a native function. Otherwise, we throw this exception. And then we check to see if the bridge is not equal to null. Now, if you guys remember, we just looked over how to statically link a function. So if the bridge is not equal to null, that means it's already been linked. So then what we do is we set up the method stack, which is, we've already gone over this function. This is the same function that the execute method function uses. And this is why I broke this code out into this function, because it's used in two different places. So if I go back, so once we set up the method stack, then we want to then just basically say methods at address dot bridge, pass in the link address that the function is connected to, which will then call into the main function that is residing inside of the, what is it, native mapping? Yeah. So it'll call into this SNB main with the appropriate proc address, and we will then call the subsequent function that is linked with that actual function provided by the link proc function up here. So that's kind of the full circle. And otherwise, or after that, we return the method. So we just call return method as normal, because obviously, it's not going to handle that automatically. And that's it. Now, in the case where we don't have the bridge, that means we need to actually link it on demand. So what I do is I call a function called locate bridge and cross. This basically does the exact same crap. And in fact, I'm actually going to be changing this out to just simply calling the link function, where I pass the full name of the method and then it links it dynamically. But there's literally no difference here. The only difference that this does in place of the actual link function is when we actually assign the SMB and we actually link the actual code, then we just literally call it inside this function. So after we set the link address, we set up the stack, we call the bridge with the link address, and then we return the method. And I'm not breaking out of here, so I'm going to hit the break. Now, you should only get this exception down here, unsatisfied link exception, if you were not able to successfully link the function. But if you were able to link it and you try to access the bridge function, and if that for whatever reason wasn't present, then you can still get the unsatisfied link exception but that should never happen. So assuming that you have all of your systems in place, ideally you just would not be able to link it, and that's pretty much it. So I think that's everything. So that's the full source code for how to actually link a file. So let's actually get back to the original video. So now let's actually look to see kind of how this stuff works. So we're going to start to get into a little bit of, I mean, the system overall is pretty simple, and there's a lot of crap here when it comes to the Sharp native bridge. I don't want you guys to get overwhelmed with this video. I want you to just know that there's very simple components to the overall system, and anything additional is just additive stuff. So you're not going to have to do everything that I'm going to be showing you guys in today's episode, because again, it's just based off of how my programming language works. And you can, of course, pick how you want yours to work based on your system. So, as I've mentioned before, this runs off of a contractual based system, meaning that we are expecting to run on a contract. So, I basically wrote the base level code here for the entire system to work, and then it just kind of builds on from there. So, the way it works is I have a SNB link proc to actually link the function, and then I have an SNB main. The SNB main is going to be the Sharp Native Bridge main. You can kind of think of this function exactly like the system interrupt function. Literally, my entire programming language runs just like the way that I handle system interrupts in my virtual machine. Now, I know some of you are thinking, so if let's go to an actual example here. So if I go to, do I have an example? And generated and native mapping.cpp. And if I scroll down, way down, it should be at the very bottom. Yeah, so I have this SMB main, and this is all generated code, by the way. I did not write any of this code. This is generated by my compiler. But you can see here that in the SMB main, you pass it a proc address, and you call a bunch of functions. This stuff is not slow. Like, I don't want you guys to think, oh, well, what if this system is slow, or what if it's not fast enough? As you guys know, I am using the system on a Raspberry Pi, and in fact, I'm using this system on a Raspberry Pi Zero. Now, I don't know if any of you guys have ever programmed on a Raspberry Pi Zero, but it's not the fastest machine in the world. In fact, I think the clock speed is like 1 gigahertz or something. It's very slow. So with that in mind, I am calling functions in my Sharp Native Bridge thousands of times every so often, and I have tons of tasks and multi-threading stuff that's running in the background. I have an entire GUI system for my controller that runs at 32 FPS, so it's constantly updating a screen 30 times a second. I also have tons of networking code that's doing lots of interfacing with network devices. It's a lot of crap, and it runs just fine. I have no issues. There's never any hitches, and if there is a hitch, it's because of the garbage collector. So you don't have to worry about this system being slow. But with that out of the way, let's actually see. So the way it works is when it comes time to actually link your function, we're going to use what's called a SNB link proc. Now, the reason why we have this link proc function, this works exactly like a DLL does. When you reference a DLL, you're saying, give me a certain function, right? And where was it at? So if I go to, what is it, smb.h, when you say load function, you're passing it a proc address, you're passing it the actual reference to the handle and the name of the function. We're literally doing the exact same thing by, if I go back up to native mapping, by literally just passing it the function name, and we're comparing it against all the function names that the current DLL has access to in the Sharp Native Bridge. And depending on that, we're going to return an address of that function at the time of compilation. Now, the reason why I do it this way, and this is the preferred way, because addresses change from build to build. Now, as I mentioned before, I do have, position independent code, so things typically don't change. But let's say if I go back to the syntax file, let's say we have this native foo function, right? And then I define a function right above it called, I don't know, sum underscore function. Well, if the address of this function was 10, the address is now 11 because the compiler ran into this function before it ran into this function. So assuming that this situation happens, it's a huge pain in the ass because you have to then recompile your entire DLL. So in an effort to curtail that, basically I'm leaving it up to the user to say either you need to know what you're doing, otherwise you're going to get seg faults. So this is a little bit less safe, but if we're being honest, it's C++. So this is the system that I have. Now, one other thing you probably could do is say and params is equal to param count. So like you can pass in a int of param count, and you can make sure that the parameters is matching for this specific function. So param count, let's say this function had 4 params. So we could say if the function name that we're trying to request and link is in fact setup and the parameters that we're passing in for the setup has the same amount of parameters as when we compiled the DLL, matching it to both the high and low level, then we should be good, but I don't really do that. This works just fine for me. So once we link it, we are going to save this little value inside of the actual function. So if I go up to symbols, so if I go to symbols and then method.h, and you can see here that I have both the link address and bridge. So the link address is going to be referencing the address that's returned from the DLL, and then the bridge function is going to be referenced to the physical address of the function inside the DLL referencing the SNB main. So when it comes time to actually call the function, literally when I call the foo function and I pass in foo, I'm going to push whatever I need to push onto the stack, and then literally I'm going to call that actual function here. And this is going to then call a function called call, and then it has a specific naming format. So I have basically the module name first, and then the class name, and then the function name. So that's how it works. Also, by the way, if any of you guys are wondering, well, what if you have like, I don't know, a word that is basically a reserved word in C++? I have protections for that. So we'll see that later on when we get to the compiler side. But like, let's say you have a class called, I don't know, goto or something. Even though that is a keyword in my programming language, let's say we had a class name that was named something that isn't a keyword in my language but is in C++. I have protections against that, so don't have to worry about that. We'll see that later on. But basically, we're going to then call the function. And this function is defined inside of a class called native mapping. Native mapping is going to represent literally the entire programming language bridged from the high level to the low level. So whenever you are compiling the source code, when we want to actually generate all these files, not only are we going to generate code necessary to actually successfully call the native functions, we're also going to generate code to call every single other function in the programming language. So that way it makes the user's life easier to call one of these functions back at the high level. So, you can kind of see here. Now, here's kind of where it gets into my own language specific things. So if you guys remember, the contract of how this works is the exe says to the DLL, I want you to call foo. And then the DLL then subsequently says, foo or exe, I want you to give me field at, index of 0 or whatever on the stack. It supplies that, and then you can do whatever you need to do with that field. So this kind of works in the same way. You can see here that I call one of my internal functions that we assigned at the handshaking stage, and I'm basically saying get frame pointer number at 0. What that does is that creates a variable, which we'll go over in a second, and it's basically allowing us to, this is some GPIO stuff for like my Raspberry Pi. This is just a quick example. This is not representative of the actual code here. This is just some old code that I scrapped from my drone project. But we're saying, give me the numeric value off the stack at frame pointer plus 0, and then also give me the second numeric value of the stack from frame pointer plus 1. So, and then we have tons of other stuff in here. I mean, all this stuff is generated and it's based off of my programming language. So hopefully that made sense for you guys. It's not going to come full circle until we get to the actual compiler stage. So let's just keep going on. So once you kind of have that basic concept of how that works, now it's time to actually finish writing all the stuff that we have to write on the virtual machine side. So now it's time to write all of the functions. So I'm not really going to go through all of these functions here because this is based off of my programming language and you're not going to have the exact same functions that I'm going to have because your language is going to be different than mine. But I'll show you some examples. So I have basic ways for me to increment references and decrement references of objects. And again, remember, this is all needing to happen on the executable side because the executable is guaranteed to understand the bitmap layout for each object properly so we don't get any weird errors. I can also get, again, a numeric value off the stack, so it returns the address of the double that is pointing to a specific address on the stack. And this literally allows us to manipulate the stack directly and, modify the values in those doubles. I also have a way to get fields. So if you pass it an object, you can pass it the name of the actual field. And again, this is very bad. You don't want to pass a constant string, and I'm actually going to be working on fixing this. You want to pass it a constant char pointer of a name because then that's going to basically guarantee that we can read the data inside of here. So you'd also have to pass the int of the length of the actual string, whatever, so you can actually do whatever you need to do. But I'm going to make that change later on. But this is another one, and then of course we have others as well, like incrementing the stack, decrementing the stack, and just more. So once you create all those basic functions, then it's time to create what I call the API side of your actual bridge. So this is where it gets into just, again, a bunch of random crap that you're going to need to do based on your own programming language. So I'm going to go over just a few things here. It's quite messy. So basically, what I have in my programming language is I created two type defs. Objects are referenced as void pointers. And I also have var arrays as well, references objects. And this is just a way for me to reference, actual data inside of functions. So another thing I want you guys to realize is whenever it comes to, so let me go back up to the native mapping.h. Whenever it comes to actually having objects, so I'm going to say objects space. So you can see here that the way it works is, for instance, this is the enum class, right? And this is a basic example of a operator overload. So I say operator $ equals underscore equals 2. Now, because this is an overloaded function and each object is not distinguished, like it's just a bunch of void pointers, I have, 0, 1, 2, 3, blah, blah, blah. If you have multiples of the same function, so if that makes any sense, just to separate each function. Because all the types are the same. But you can see here that for functions where we have an instance, we have to pass in the instance first and then the actual field after that. So this is kind of an example of us using objects. And again, we'll get into the specifics of how I rename things. Like, this used to be operator equals, right? That used to be the actual name of the actual function, but obviously that's not going to work because it just highlighted it, so you have to rename those values. So we'll get into that later. But back to the API. So if you guys are wondering, so I have a concept of scopes in my programming language. Here's how it works, right? So can I actually split this? I'm going to try to split this vertically. So if I go to the SMB API, so you can see here that I have scope begin, std enum, and then scope end, and in between there I have stuff related to that scope. All scopes are representing are basically just namespaces. So, and I do it in a way where it's pretty legible. So if you're basically saying you have a scope inside the module std and a class of throwable. Well, what happens if you have, I don't know, like a generic class? So if I do list and then $, you can see here that this is kind of how I do it. So For renaming values of, list of type string, I basically use $sign, so I say list $sign std underscore string $sign. And I have to put the full name. I can't just say list of string because what string class are we referencing? So I put the full name of the actual class in between the $signs representing each of these brackets. And when it comes to beginning a scope, basically I use this crap that I found on Stack Overflow. Basically, it's a way to allow the user to receive errors as they're doing things. So if the user, I don't know, puts some extra crap in here, they're going to get an actual compile time error saying too many arguments provided. And it's just a nice, helpful way to let the user know that they screwed up. And I also put an example here of what they need to do to make it actually make sense. So the way that I do this is I say scope begin, three dots. I create a get macro function or define statement which allows you to supply a macro that takes a dynamic amount of parameters. In my case, I'm taking up to 5 parameters. And for each one, for scope, I have 2 types of scopes. I have the regular scope, which is scope of 1, where you just pass in the module. So what I do is I say namespace and I concat 2 values at compile time based on whatever you put in here. So what this is going to do, where if I go all the way to the top, where you can see I have scope begin of std, this is going to create a namespace of std underscore global. As you can see here, I'm concatenating the module name and underscore global. So that's kind of what it does. And then I also have another concept where if you actually pass in the module and the class, then this is going to create a namespace. So if I do name of std underscore throwable. So that is now going to be the namespace's name. So hopefully that makes sense. This is just a quick way for me to rename those values, and you can see here that I'm doing that for this. So that's kind of the format. Now, when it comes to importing was kind of a attempt for me to make it a little bit closer to Sharp. So importing works in the same way. So if we try to import something like, let's say, import the std module, we're basically just saying using namespace std underscore global. That's literally all we're doing. But I can't say, using namespace of std because that is used by C++. That's why I opted to put the underscore global after the module name. So you can import the std module, and this obfuscates how importing and scopes kind of work away from the user. And if you also want to, so I have an additional formatting for importing. If you say std, let's say exception, so you can import the std exception class, which would then basically import, again, using namespace of std underscore exception. So that's kind of how it works. It works the exact same way that scope does. So I have each individual thing based on what I need to do. And for the macro, I pass it this var args, and then I just pass it each value. So I have the number based on how many arguments. So import 3 is for 3 args, import 4 is for 4 args, and 5. So I support up to giving the user a dynamic error up to 5 arguments. And for import 1 and 2, again, it has 1 or 2 arguments. So I just fill it in here directly. And I do it like so, and that's pretty much it. I also have these exported virtual functions for the actual API to do the internal function calls. And down here, if I continue scrolling down, now again, this gets more into my own language specific things, but now we're at a point to where we have literally infinite possibilities. We can convert a var array to a string. Now I created this var array class, which basically represents the higher level version of a var array. So if I were to go back to syntax and I were to create a num, and it's a var array, that's representing this value at the high level in C++. So as you can see here, there's like several different functions. You can do simple stuff like assigning the value, which basically just assigns the first value in the list. You can also do things like checking whether or not it's equal to a string or whatever. So there's tons of things here, And I'm not going to go through it because this video will be too long, but again, this is where it gets into your own language. Do whatever you want. I have this very nice get function, which is a template function, which allows me to basically get a field and I get to basically cast it to the type of data. So if I go back to foo, again, if I have this object here, I can say, I don't know, var, right? And then the, I don't know, x field, and then I can say get a var from the foo class and get the field of x. And this basically allows it to be more readable to, a human, to where it just kind of flows, right? So it's really nice. And the way that I do that is, if I go back to the API, I basically get the field by passing it the field name, and then I call some more internal functions like getting the var pointer, which returns an object, and this is basically getting the numeric value of that actual pointer. And the get function is assumed to be used for getting like numeric values. Now, I also have pre-configured templates for getting like a var array, which does something different. So it gets the pointer of the actual array, it gets the size of the array, and passes it the field object. I also have one for getting objects. I just return the field or the physical pointer of the address of that field as an object. So again, there's tons of crap that I do here. I have the ability to increment and decrement references. And the way that I basically set up my API is to not have the user worry about references, because they shouldn't have to, right? Like if they assign an object to a value, they shouldn't have to care about getting rid of references and so on. And if you guys want to kind of see how various different things work in the actual Sharp Native Bridge API, I definitely consider looking at one or even both of my demo videos that explains in detail basically all these functions that I'm kind of showing you guys now. Nothing really has changed, so all this stuff is the same, so those videos are valid. But like I said, I'm not going to go over this because it would be taking too long. Now, one thing I will go over though is I did recently add an exception system supporting into the actual programming language. Now, the way that this works is basically if I go to the virtual machine, if you remember, every time when we call into the DLL function and we have to call back into the executable, that's going to require us to do a bunch of stuff. Well, there's a potential that we could be trying to do something that could potentially get us in trouble and get an exception. So if I go here, we can see that we have, like, for instance, call, right? What if we call a function and it throws an exception? Well, what's going to happen is we're going to catch that exception. We're going to send an exception signal. And what's going to happen is basically after we call that function, we're going to check to see if we have an exception. So we're going to do an exception check, which is going to return a Boolean. And so let me see. So if I go to the actual source code, you can see here, for example, let's say we create a big ass array of data. When we call exception check, we're going to then just simply throw an exception, and we're going to just request that exception object that's been thrown from the executable. And that's it. And it's literally that simple. And then if the user wants to do something with that exception, they can either clear the exception. So if I go to the actual source code, there's going to be a clear exception function. And if they want to throw an exception, then they can just pass an object, which then passes that to the executable to throw that actual exception. So it's pretty simple and it's pretty straightforward. Now, one more thing that I will say that you will have to do is you will have to trail that source code all the way back to the main function of the actual DLL. Meaning that so if I go to, what is it, native mapping, and here you can see in the SNB main, I'm trying some data and then I'm catching it. So as we call into this function, if we don't catch an exception that's being thrown, we'll bubble up all the way before you get out of the DLL back into the executable. And then we will basically prepare the exception to be thrown after we get out of here. Guys, you do not want exceptions to travel from your DLL back up to the executable, because backtracing your source code that far, it's just not going to work. Trust me on this. So whether it be Linux or Windows, you don't want to do this. If you're going to integrate your exception system with your programming language, this is the only way you can do it. So just take my word for it. So that's going to be it for today, guys. That's pretty much everything, to be honest. There really isn't anything else we have to go over. Everything else would just be like little things here and there that are again just additive stuff that I mean it's just not really going to be that good use of you guys' time in my opinion. So that's going to be it for today. If you guys have any questions, as always, definitely put it in the comment section below. And actually, now that I'm starting to think about it, I think we're done with the virtual machine. This is pretty awesome. So we've gone over the memory garbage collection system. We've gone over how to build a just-in-time compiler. We've talked about the entire symbol table. We've talked about the exception system, the multi-threading platform, as well as the Sharp native bridge. And yeah, so that's literally it. So the next episode, we're actually going to be going back to the compiler for the first time. So definitely look out for that. That video is going to be this Friday. Of course, if you guys would love to help support the channel, you can always head over to the GitHub repository at andrewdevcity/sharp. And when you do, definitely watch, star, and fork this repository. That gives this language a ton of more visibility and let other developers know this language exists. Also, if you guys are curious about some of the stuff that I'm looking to add in the future or just stuff that I'm working on now, you can head over to the roadmap section and there's some pretty decent descriptions on what I've been up to in real time with the actual programming language. So this is a really nice view to just kind of see what I've been up to. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing. And until next time, see you guys later.